Okay. So last week we talked about the UnionFind algorithm, and we just saw how you can use it to solve a variety of problems, including the number of connected components. How to even detect if there's a cycle in a graph, right? That's another algorithm you can use. So, for instance, if I have a graph this way, like if I have node A, if I have node B, I have node C, and I have node D, right? And let's say I have uh I have something like this, right? And let's add a third edge here, right? So this green one ends up introducing a cycle, right? So let's say you have it, for now, just think of it as undirected, right? So this one introduces a cycle. I mean, it could have been any of them, but it could have been any of the other edges, but let's just choose the green one, produces cycle. So how can we use the UnionFind algorithm to do it? So when we take A and D, right, we find their parents at the start, they're both, their own parents. So we union them, right? So we join this edge. Then say we take A and B, right? We take A and B, then we also union them, right? So now we get something like A is joined to both B and D, right? We get that. Then we take, say, B and C, we take B and C, then we union them, right? We union B and C, so they both now answer to A, right? They both now answer to A. So both B and C answer to A, D also answers to A, right? Then we take D and C to also union them. But when you take D and C, if you check their parents, right? If you check the parents of both D and C, they already have the same parents. That means if you try to union them again, that is going to cause a cycle, right? Because they already have the same parents. So the UnionFind algorithm can be adapted to identify there's a cycle in a graph. And the algorithm is simply, try to union them. And if at any point you get their parents and they have the same parents, that tells you they're already joined. And joining them again is going to introduce, a cycle in your graph. And then we went through, other applications. And today we will learn something called the minimum spanning tree, and we will beautifully adapt the UnionFind algorithm again. So let's go to the topic, that is minimum spanning tree, right? It's a very cool stuff. So let's see something. So we've already learned what trees are, right? So we said trees are basically graphs, except they are undirected, they are fully connected, and they're acyclic, right? So trees can have no cycles, right? Trees cannot have a cycle. All trees are acyclic. This is what I call a tree, right? This is basically a tree. So it's possible that you'll be given a graph, right? So let's say you'll be given a graph. So let's connect to this last edge here. Let's connect to this edge here, right? So this does not make it a tree now, right? This makes it a graph. A tree is a graph. Then we have this one too here, right? So this is a graph. This is a graph, right? And then the question is, I want to create a tree out of this graph with some constraint. What is the constraint? I want my tree to be as cheapest as possible, right? As cheapest as possible. So let's define the concept of cheap. So cheap simply means the total sum of the edge weight must be minimum. So we know these are the edges. These are the edges. These lines where we are the edges. So we're going to assign weights, right? Or some values to the edges. So now we can just use, integers, unsigned integers. We can use, let's say 4, let 3 be here, let 2 be here, let 8 be here, let 6 be here, let 5 be here, let 4 to be here, let 12 to be here, let 1 to be here, let 3 to be here, right? And now taking this graph, we want to construct a tree out of it. We want that resulting tree to be as cheap as possible, right? So that's the whole problem. Given a graph, right, where the edges have weight, construct for me a tree that is as cheap as possible. And then we've already gone through the definition of a tree. One, we said that a tree must be connected, right? That means that there must be a path, from a node to all the other nodes, right? It must be connected. Two, it must be acyclic, right? That means that there must be no cycle, right? We can forget the undirected part for now. But yeah, so let's just focus on these two things, right? So let's see how we can construct this. Now, can someone just look at this graph and just tell me how we can do that? Just look at this graph. I think we should label let's label the nodes. So let's just call this node A, B, C, D, E, F, G, and H, right? So how do you think we can do this? Anyone? How do you think we can construct a tree out of this graph? How can we do that? How can we do that? Anyone? Any ideas? So it can be like, so first of all, we can start. First of all, I just want you to know that the final tree you construct must contain all the nodes, right? So it must be connected. Every single node must be in the tree. Every single node must be in the tree. So let's just do something. Can someone choose any node we can select first? which node should we select first? Or which edge? Any of them works, right? So this is the node, but this is an edge. So if you say edge, you're going to be like edge AB. If you say node, you just mention one. So anyone, which one should we select first? Anyone. We want it to be as cheap as possible. So which one should we select first? Anyone. If someone is talking, they are muted. So, okay, something in the chat. Okay, we should select node A. Good, good, good. And honestly, you can select any node because all the nodes will have to eventually be in, right? So let's select node A. So we selected node A. Yes, anyone. Which one should we select again? Okay, now let's do edges. Which edges should we select? So, Fifi, which edge should we select? Instead of node, give us edges. Which edge should we select? Which edge should we select? EG. Okay, somebody said EG. Let's select EG. Where is E? E is here, and then there's G here. Okay, so we have E and G here. And the cost of that is 6. Yes, anyone else? Anyone? Please, let's hurry. Just take a good look at the thing and we just want it to be as cheap as possible, right? And we said all nodes are going to be in. We'll go through a formal algorithm to do that, but don't think about an algorithm. It's just like the same way you are thinking about it, right? So which one did we select? Anyone? Can anyone give me another edge we should select? Anyone? I need about 5 from you before we continue. So anyone, which edge should we select? We selected the edge EG, right? That is EG. This one. We are like, this should be part of our tree. Which one else? Which one else? Anyone? You can type it in the chat. You can unmute yourself and talk. So the problem is we have this graph here, right? We have this graph here. We want to create a tree out of this graph. We said a tree is simply a graph, except, there's no cycle, right? But this thing has a cycle. As you can see, there's a cycle here. This one forms a cycle. You can, go around it. You don't want this cycle, right? So that is one thing. And everything must be connected, right? And all the nodes must be present inside. So given this graph, how can we create, a non-cyclic thing, that is a tree from it? But then the edges, the cumulative sum of the weights of the edges must be as cheap as possible, right? Must be as cheap as possible. The number of algorithms, we can go through one quickly, and then you can give me the other one. But I just want a few edges from you. What other edge should we select? What other edge should we select? What other edge? Okay, one person should give me an extra edge. CD, C and D. Why is C and D? Good, good. Exactly. C and D would definitely be in. So we have C here, and then D here, right? So this will definitely be in, and it has a cost of 1. Okay, so let's just go through it very quickly, and let's go through the algorithms. I think we're actually behind time. I wanted to close early today. So to select it, we're going to consider a number of algorithms. One algorithm we're going to consider, is Prim's algorithm. Prim's algorithm. The other is Kruskal's algorithm. And then we consider, a third one. That is kind of like, let me just call it removal. Like remove, biggest edge weights. Biggest weights. Okay, so let's look at the algorithms we're going to basically consider here. So for Prim's algorithm, I'll be everyone following, please, we're going through an algorithm now, so follow me as much as you can. So Prim's algorithm, so as you can see here, the first one to think about is the fact that every node is supposed to be in. Don't think about these algorithms for now. Just follow what I'm trying to tell you right now. It's going to really help. So don't think about the algorithms here, but then have in mind that every node is going to be in. So I just want you to select any node, right? And ask yourself, what is the cheapest way to get to this node? Right? So select any node at all you want. And the question just says, what is the cheapest way to get to this node, right? So if I choose, let's say, node C, let's assume we choose node C here, right? Now, the cheapest way to get to node C, can be, using this one, right? Using this route we have here, right? Taking this route 1, right? The cheapest way to get to node C. Does it make sense? Does it make sense? Does it make sense to everyone? Good. Then you can take another node and ask yourself, what is the cheapest way? Where you're doing a very greedy thing here, greedy algorithm. That is like, just set the greedy rule is find the cheapest way to get to that node, right? So let's choose another node A. I choose node A, and what is the cheapest way to get to node A, right? There, maybe you can use this edge that is 3. You can use this one that is 8. You can use this one that is 4, right? That is 4. So 3, 8, 4. You're like, okay, let's go for this guy. 3 is the cheapest one here, right? Then we can, go on and go on and go on and go on and go on. But then this is what we call a greedy algorithm. This is something called a greedy algorithm. So how greedy algorithms work is that you do something called, the greedy rule. The greedy rule. And then you apply that greedy rule consecutively, right? So yeah, our greedy rule was choose any node that hasn't been chosen before and select the cheapest way to get to that node. And that is all, right? That is basically the greedy rule we selected. Sometimes greedy rules have issues, right? They sometimes don't give the very optimal solution. That is something we will see later. Sometimes they work, sometimes they don't give you the most optimal solution, that is out there. I think even this one, we can actually try to create, let's see if we can get a case where this greedy rule we did here may not work. So let's say we have 3 here. Let's say we have 15 here. Let's say we have 8 here. Let's say we have 20 here. Actually, this will work. Actually, we'll construct other ones out of it. Let's just go on to the algorithms. Okay, so now let's go over Prim's algorithm, which is just going to be similar to what we just did here. So for Prim's algorithm, what we are going to simply do is that we're going to start with the similar analogy to the greedy rule we used. And we're just going to choose, why is this thing not doing it? Okay, so Prim's algorithm says that choose any node you want that has not already been chosen, right? And then choose, consider all its edges and choose the cheapest one, just like we did for the greedy rule. So here we choose this one, right? And then you circle the node that it connects to, right? And then, so here we have this edge 3, and then we have this edge 1, right? These are two we consider, then we choose the cheapest one, that is 1. Then we consider nodes C and D again. Then we choose the cheapest edge connecting them. Here, the edges we're going to consider are edge 3 and edge 12. The cheapest one is 3, so we choose 3. Then we select B. Then again, we consider all the edges that connect to these nodes we have chosen. So here we have 4 here, and then 2, we have 12 here. Choose the cheapest one. So far it doesn't form a cycle. Here we choose 4. You choose the 4 here. And then we circle node A. Then what do we do again? We consider, the edges again, connecting to the nodes we have chosen. So here we have, let's remove the ones we have selected. 12 is still standing. We have 12 here. We have 3, it connects to A. We have 8 here, it connects to A, right? And then we said choose the cheapest one. I think 3 is the cheapest one. We choose 3, right? And then that means we select node 4 here. This is H. Oops, H, not 4. Then we go on again. So now the ones we are considering, right, are 2, 12, and 8. And again, Prim says choose the cheapest one, right? So then we choose, this guy here, and then we select this guy, select this node here, right? And then, so we're done with this one, and then we consider, the next edges that are connected to these guys, right? So here we have this, and we have this, and then we have this one also, right? Then again, Prim says choose the cheapest edge. So first, does not form a cycle, add them. So here, 5 is the cheapest. Is it 5? 5 is the cheapest edge, right? 5 is the cheapest edge. We are considering 8 because 8 is connected to A, right? 6, 6 is connected to G, and G has been chosen. 5 has been chosen, and then 12, right? And indeed, 5 is the cheapest edge. So we choose 5, right? And then we select node F. We select node F now. Does it make sense? And then it says again, choose the cheapest edge, right? That connects to the nodes we have already selected. And here, as you can see, we have this 5 here, right? And then we have, this 4 here, and then we have 6 and 8. And obviously, I think 4 is the cheapest, right? 4 is the cheapest here. So 4 is the cheapest. So then we choose 4 again, then we select node E, right? Okay, is everyone following? Does the algorithm make sense? So we started with choosing any random node, right? Any random node. Then you consider all the edges connected to, that node. And then you choose, the cheapest one, right? Then that forms an edge. Then you consider those 2 nodes you have now and choose the cheapest edge that connects them, which you have not chosen. If adding them does not form a cycle, then you include that edge. So now let's proceed with the algorithm. So now we have a number of edges to consider. We have this edge that has not been chosen. We have this edge that has not been chosen. We have this edge that has not been chosen. The cheapest one is, I think, this guy here. This is the cheapest one, I think. Right, this is the cheapest one, the 6 here. But then you realize that the moment we add this 6, once we add this 6, we're going to get a cycle because this one has been chosen. So G to F has been chosen, F to E has been chosen. If you add 6, right, E to G, you get a cycle here. That means we cannot add this one. So we can remove it safely. We can remove this one. Then, we could have solved the algorithm already, but I just wanted to follow like the execution. Then here, we consider the next cheapest one. I think is 8, right? 8. But if you choose 8, you end up getting a cycle, right? This whole thing becomes a cycle. So we cannot choose 8. Therefore, we remove this guy 8 here. We remove 8. Then we go ahead. We're like, okay, 12 is the only one remaining. If you choose 12 also, you get a cycle. Therefore, we cannot choose 12. And then remove the 12, right? Remove 12 now. And then that is basically, a tree. We formed a tree here. How do we know it is a tree? Number one, it is connected. Every node is connected. There's a path from each node to any other node, right? It is fully connected. 2, it is acyclic, right? There's no cycle. As you can see, there's no cycle. You can go and come back to where you started from. There's no cycle. And 3, every single node is present in our tree, right? Every single node is present in our tree. Now, someone could have noticed that at the part where we got every node, circled in black, we could have stopped the algorithm. And that is true. You can just continue the Prim's algorithm by simply saying that while, the number of selected, or you can simply say while every node is selected, right? So if I want to enter the while loop, it's while not every node is selected, right? So while there's a certain node that's not been selected, then you execute the algorithm, right? But if every node is selected and then you stop, right? So if you can see, the Prim's algorithm is greedy. How is it greedy? It's greedy in the sense that, it selects the first node, selects any node can be the first node, considers all its neighbors, right? All the edges connected to it, selects the cheapest edge, right? So let's say we select C. Then it will consider both C and D. Note, it does not consider only for C. It considers, the edges for all, the selected nodes, right? Then choose the cheapest one amongst them, and then just go on to that. Someone said, is there a maximum number of edges to be considered? No, all edges have to be considered. So far as the edge is connected to any of the selected nodes, right? So if I have, these two as our selected nodes, and they have like, all these edges connected to them this way, we're going to consider these 3 edges and these 3 edges, and then choose the cheapest one. So maybe, this is the cheapest one. We'll then choose this one next. Maybe we choose this one next. That is how Prim's algorithm works. If you can look at it, Prim's algorithm builds the tree. Like, it continues to build the tree consecutively, right? It builds the tree. Like, the tree just continues to build, right? It's like it just continues to expand, like spread its wings. That is how Prim's algorithm works. Does Prim's algorithm make sense to everyone? Does this algorithm make sense? Does it make sense? Anyone? Does the algorithm make sense? Does the algorithm make sense? Okay, not fully. Let's go very briefly once again. So it's a Prim's algorithm. How it works is you start with your graph, right? Start with your graph. So this is my graph. So let's say this node A. Let's go over it one more time with a very simple graph. Then let's assign edge weights. Can you choose a different node at the center? Yes, you can choose any node to start with. It's an arbitrary node, right? Because at the end, every node is going to have to be in the tree. Right? We said for a tree, every node must be in. Every single node must be in. So it doesn't matter which node you start the algorithm from. It's still going to work, right? So if we have this right now, let's just use another execution of it. So let's say we have 3, 4, 7, 5, then we have like 8, right? We can choose any node at all to start with, right? So here I can choose any node. I can choose like node C. If I choose node C, I'll consider all the edges of node C, all the neighbors of node C. So here it has only one, right? It has only this guy. And then we choose, we have to choose this guy. So that is like the cheapest. You can think of it as the cheapest way to get to node C, right? So we choose this guy, then we circle D. So D has been chosen now. And now the nodes I've chosen are C and D. Then I'll consider all other edges of connecting to C and D. That is not selected, right? So here, those edges are this edge because it's connected to D, and this edge because it's also connected to D, right? C has no other remaining edge, right? C has no other remaining edge. So I'm going to choose, so I have just these two to consider. So I'm going to choose the cheapest one here. That is this guy here, right? I'm going to choose this cheapest one here, right? So then I'll choose node E, right? And then the next thing is I'll consider once again this guy here, right? This guy here. And then, I'll consider this guy here and then this guy here. These two, 4 and 5. I'll consider 4 and 5 here, right? Then I'll choose the cheapest one amongst them. Then I'll choose this guy, right? Then I'll choose this guy here, right? That's basically how the algorithm works. Then here, I'm almost done. I have this one left and this one left, right? Because they're both connecting to nodes that have already been chosen. And then I'll choose, this guy here. And then I'm done. Why am I done? I'm done because every single node has been chosen. Every single node has been chosen. All the nodes have been circled in black. Every single node has been chosen. And it was obvious, right? That the cheapest one, right? The cheapest tree would exclude like the biggest, like this 7 here. So the tree is simply this minus this guy, and this is the tree. Does that make sense? Any node could have been chosen from the start, right? Because eventually you end up selecting every single node. Does that make sense? That makes sense. Good stuff. Okay, let's go to the next algorithm. This is what we call the Prim's algorithm. So we call Prim's algorithm. It's actually not bad. It makes sense, and it's a greedy algorithm. Now let's go to the next algorithm called Kruskal's algorithm. So Kruskal's algorithm is kind of like, I would say more relaxed. I don't know, maybe more difficult, maybe easier. Depends on you. Okay, so let's see how Kruskal's algorithm works. So let's draw another graph here. And now let's, assign weight 3, 4, 5, 6, 7, let's say 8. Then let's label them A, B, C, and D, and E. Now note, in Prim's algorithm, if you choose the minimum one, if adding it will cause a cycle, you ignore it, right? You only choose and add it if it will not cause a cycle. So like the first one you saw, right? There was a certain, edge we saw, we didn't add them because adding them would cause a cycle. So the conditions are two. It must be the cheapest edge, and adding it does not cause a cycle. Then you can choose it, right? Let's look at Kruskal's algorithm. Kruskal's algorithm is a bit, very, very, very interesting too. Kruskal is like, don't think about nodes. Kruskal, don't think about nodes. Just think about edges, right? So just choose the cheapest edge. So look at the graph and just choose the cheapest edge. That's what Kruskal is telling us. So here, my cheapest edge seems to be this edge, 3. It's like, okay, now choose 3. So if I choose 3, 3 connects node A and E. So I'll circle those two. Kruskal's like, okay, well done. Now, again, choose the cheapest edge, right? And I'm like, the cheapest edge seems to be 4. It's like, okay, then choose 4, right? It's quite unfortunate. You know what? Let's move the 5 from here to here. Let's move the 5 to because I want to show you something. Let's move the 7 here. Then Kruskal is once again choose the cheapest edge, right? Here, the cheapest edge is this guy. Oops, let's wait. Let me bring it back. The cheapest edge is this guy. Now, can you see that with Kruskal's algorithm, the graph can be built in different areas, then they all join together, right? If in Prim's algorithm, you realize that we were building the thing like it was just like spreading, right? We were choosing the edges that are connected to the nodes we have already chosen. But for Kruskal, he's like, just pick the minimum edge. And if adding it will not cause a cycle, just add it, right? So again, as you can see, we don't have, a cycle. We don't have a cycle yet. So Kruskal is like, choose the minimum edge again. And I think that is 6, right? 6 is the minimum edge because we've not chosen 8 and 6 and 7. So 6 is the minimum one. Then we choose 6. Then once we choose 6, you can see that all our nodes have been selected, right? Node A has been selected, node B has been selected, node C has been selected, node D selected, node E selected. And then Kruskal is like, you are done, right? You are done. How am I done? If I choose the next cheapest edge, that is 7, I'm going to get a cycle. Can you see? Choosing 7 causes a cycle because they're going to get this cycle here, right? So we are done. So we can easily remove all these ones we didn't choose. And then we have our tree here. And that's Kruskal's algorithm. So Kruskal's algorithm is, hey, take your graph and then simply, choose the cheapest edges and just connect them together. If adding the edge does not introduce a cycle, just connect it, right? And Prim is like, nope, first choose a node, right? Then after you choose that node, right, consider the edges connecting to it, choose the cheapest one, and then continue to expand it forward. Do the two algorithms make sense? Do they make sense? Do these two algorithms make sense? Is anyone confused? Do these two algorithms make sense? Good stuff. Then there's another algorithm. That is the last one, right? Let's look at the last one. Well, let me show you the last one. Then I'll show you why we prefer Prim's and Kruskal's algorithm. So the last algorithm, it's something like this. So that is, take your graph again. Let's take our graph again. Then the last algorithm, it's actually, I feel like it's the most intuitive one. But it's actually also not the most efficient one, and I'll show you why it's not the most efficient one. So let's say we have 5, 4, 12, 18, let's say 6, let's say there's 9, right? A, B, C, and D. Then the last algorithms is like this. The last algorithm says that take the most expensive edge, right? Take the most expensive edge and then remove it, right? You take the most expensive edge and then remove it. So here I'm going to take the most expensive edge, that is 12. Then I remove my 12. So I remove the 12 here and only remove it if removing it will not disconnect, the, what do you call it? The graph. So what I mean by disconnect is this. So if I have this, right? assume I have this, right? And I have, let's say, 12, and I have 8, and I have 16 here, right? If I remove this 16 guy, assuming I remove 16, that is the most expensive, the graph is still connected, right? Like I can still, visit every node, starting at any node. But if I start at this node, I can get to all the other nodes, right? So take the edge with the biggest weight and remove it. So far, does not disconnect the graph, right? So here I can remove 12 because removing 12 does not disconnect the graph. Then again, oops, I should have removed 18 first. 18 was the biggest. So I remove 18 because 18 doesn't disconnect the graph. It's like, okay, now choose the next bigger one again and remove it. And I'll choose 12. That's not disconnected the graph. Good. Now, the next biggest is 9, but I cannot remove 9, right? Because the moment I remove 9, my graph gets disconnected. I get this graph, and that is wrong because a tree must be connected, right? So this is wrong. So that means that I'm done. I have to leave 9. And this is, the minimum spanning tree, right? And this is the cheapest weight possible. That's something you can verify by adding the weights. Does this make sense? So these are the 3 algorithms. Does this make sense? Does this make sense? People, does this make sense? Everyone, it makes sense to everyone, right? Okay, so I'm going to show you, how to basically the implementation. The code is actually not the easiest, neither is it the hardest. But today I want us to focus on this one first, and we can actually, throw this in. Or actually, let me tell you why this one may not be the most efficient. The third one we just discussed. So we have something called a complete graph, right? So a complete graph is simply a graph that has an edge between, every 2 nodes. What I mean is, assume, you have this graph, right? So let's say you have A, B, C, and D, right? The graph is said to be complete if for every pair of nodes, there's an edge between them. So there's an edge from A to every other one, right? Then if I take D, right, there's an edge from D to every other one. If I take C, there's an edge from C to every other one. This is a complete graph, right? Now, if I want to form a tree, the question is how many of the edges am I going to remove? And the answer is a lot of them, right? So if you have a complete graph, that tail algorithm is actually very inefficient, right? Because at the end, you realize I just need 3 edges here eventually because, there are 4 nodes. By the way, if you don't know, keep this thing in mind. For every tree, right, if the number of nodes is n, right, the number of nodes is n, the number of edges is n minus 1, right? So if there are n nodes in a tree, they're going to be n minus 1 edges, right? So here I have 4 nodes. So my number of edges are going to be 3, and I just need 3 edges. But then see how many edges we have here. We have 1, 2, 3, 4, 5, 6. I have 6 edges. That means I'm going to remove 3 of them. But then think of if I had, if I had like a huge tree. By the way, this is a math formula. I think the number of edges is n times n minus 1 over 2 for a complete graph, right? So assume you have like 7 nodes, right? So assume you have 7 nodes, 1, 2, 3, 4, 5, 6, 7. You have 7 nodes for a complete graph. You know that for the tree, you just need about 6 edges. But then for a complete graph, you're going to have how many edges? Like it's a lot of edges, right? But then, for all these edges, I just need 6 of you. So if I'm doing this removal thing, I'm going to end up removing a lot of the edges. Wait, does it make sense? The inefficiency, right? Like it's going to be like Spider-Man or something, right? A lot of edges. But then you know that you just need, eventually, you're going to be left with only 6 edges. So if I do the third algorithm, right, which involves removing the most expensive one, you're going to do a lot of work, removing them, a lot of work removing them. That is why, it's not the most popular algorithm out there for minimum spanning trees. That's why we rather start with, selecting the cheapest ones first. Does that make sense? Does it make sense why the third algorithm is very computationally expensive? Because we know that at the end, you're just going to keep very few of the edges, right? So if so why don't I start from choosing the ones I want? Because after I just choose 6 of them. If I start from the ones I don't want, I may end up, choosing, deleting as many of them. Does that make sense? The others, does this make sense? Why we would not do the third, why we not do the third one? Because the third algorithm is computationally expensive, right? Especially for a complete graph. So don't forget what a complete graph is, right? For every 2 pair of nodes, there's actually an edge between them. Okay, now let's see how we can actually, implement Kruskal's algorithm. It's a very fun stuff. I'm going to use UnionFind. Yeah, I know, right? You're also excited. So let's go back to Kruskal's algorithm. Can someone tell me how the Kruskal's algorithm is? Can anyone tell me? You can type it in the chat or something. How's the Kruskal's algorithm done? When I come to say, can you use UnionFind to actually do it? To write the code. Anyone? What is Kruskal's algorithm? What does Kruskal say? What does Kruskal say?
I think people can also unmute and talk if that's faster.
Yeah, you can
You can.
So if it says you
So
take the cheapest edges and then you compare them. Yeah, exactly. Take the cheapest edge and just throw it in, right? Take the cheapest, and just join them together. Good. And we can actually do that using UnionFind algorithm. Look at how it is. How does UnionFind algorithm work if you remember? So first of all, I just want you to know something I've been saying, it really helped me when I just thought of it that way. That an edge, it's simply two pair of nodes. That's simply an edge. U comma V, right? So here it can be A comma B, right? That's an edge, right? So I don't know if we will talk about the formal definition of a graph. A graph G is simply defined as this, a pair of vertices and edges. So V is a set of edges, the set of vertices, right? So here V is equal to A, B, C, D, and E, right? And E, that's a set of edges, is equal to, there's an edge from A to, between A and E. So here I have, we usually use a pair like this, A comma E, then E and C, so I can just say C and E, then B and A, so I can say A and B, right? So this is basically how it is, right? So that's basically an edge. An edge is simply two nodes, right? Two nodes that share a line, but we simply write it like this, right? Remember the UnionFind algorithm? How the UnionFind algorithm worked was, it takes, the input was something like this, right? So we're like 1, 2, right? Then we're like 2, 4, right? Then we're like maybe 3, 6 or 3, 5. And then we're like, okay, let's union these guys, right? So we're like, let's union them. And what we will do is that we take, this guy, you try to join them together, right? That's basically the UnionFind algorithm works. Now, with the Kruskal's algorithm, right? And the minimum spanning trees, the each edge is not just node. Each edge is not just node. It has a third thing called the weight, right? The edge has an additional weight. So for the input to this question, we're going to have it as a triple. So the first two are the nodes. The last one is, let's say, the weight, right? So let's just use letters for the nodes. So A and B with weight 3, right? Then like C and E with weights, let's say 6, right? And so on and so forth. So like C and D with weight 5, right? That's basically what you're going to do. So this is the first thing. So this is how our input is going to be. Then we want to simply find the cost. So that's when the question is find the total weight. Find the total weight. Ah, find the total weight. After that, I'll show applications of this algorithm, the minimum spanning tree algorithm. Find the total weight of the MST, minimum spanning tree. So what you do is that, first of all, Kruskal's algorithm was, you first choose the cheapest edge, any of the edges that is the cheapest, then he would join them. But you know that if I have two nodes, joining them is same as UnionFind algorithm, right? That's simply what the UnionFind algorithm did for us in last week. So what Kruskal's algorithm does is, first of all, you sort them. We sort. The moment we sort, you know that the first one is going to, have the first one is going to be, the cheapest one, right? So we sort based on this guy here. You sort based on this gentleman here, the weight. Then the moment I sort based on the weight, then I'll take this guy, right? Then I'll take this one. Then I'll go and union them, right? I'll go and union them. Then I'll come to this one. Then I'll go and union them. Then I'll take this one. I'll go and union them. But remember, I have to check for cycles. And we already mentioned how we check for cycles, right? From using the UnionFind algorithm. How do we check for cycles? I actually had a sketch of it here, if you could remember. So we use this diagram, right? That assume this is your input, right? How do you check for cycles using the UnionFind algorithm? So if I take, let me just go over this very quickly once more. So to check for cycles, what I'll do is that, okay, first of all, I'm like, I want to join A and B, right? So when I join A and B, let's say we make A the champion. So B now answers to A. So we have joined A and B. Then I want to join A and D. So if I want to join A and D, I make D also answer to A. That's a UnionFind algorithm, right? Like you increase the rank. So here the rank of A is 3. The rank of this guy is 1. The rank of this guy is 1. But the parent of, everything here is A. Then now I'm like, I want to connect B and C too. So B and C, also connect B and C. But then it becomes something like this, right? So I have something like this. If you forgot the UnionFind algorithm, please watch last week's recording. Then lastly, I'm like, I want to join D and C, right? Whenever I come to join D and C, and not D and C already have the same parents A. Now when they have the same parents A, you're like, oops, that means you already joined somewhere, right? That means you already have, you already joined somewhere. Therefore, you cannot join them, right? So that's how you use the UnionFind algorithm. If you find their parents. So if you find the parent and the parents are the same, it tells you they're already connected some way, somehow. And therefore, adding the new edge is going to introduce a cycle. So that's basically how you do for the cross-calls algorithm. So we select, the edge, then you go to union them, right? By unioning, you first find their parents, and if their parents are the same, that means, hey, adding you introduce a cycle, then you discard it, right? Then you go on to the next one, then you go on to the next one. And that is basically the cross-calls algorithm. All you need is a UnionFind data structure, and that is all. Does that make sense? That makes sense. Does that make sense to the rest of you? So it's just take the input, you sort the input, take the first one, trying to union them. But before you union them, check their parent, check the parents of A and B. If they have the same parents, that means joining you is going to introduce a cycle, right? Then you can discard it. Then go on to the next one and so on and so forth. Please, if you're in here last week, watch last week's recording. It's going to really help you understand the UnionFind algorithm and this thing we just did here to answer that, right? And that is basically it. Does that make sense? Everyone, does that make sense? Does the concept of minimum spanning tree make sense? So basically, does the minimum spanning tree, right? You just have a graph, want to create a tree out of it, but the resulting, cumulative weight should be the cheapest possible. And we discussed 3 algorithms. That's Prim's algorithm. That is this guy. Then we discuss, that's this guy. Then we discuss cross-calls algorithm. That is this guy. Then we also discuss, the third one, which we say is very inefficient and can be computationally very expensive, right? Then we discussed how, you can implement, cross-calls algorithm by simply using the UnionFind data structure. Prim's algorithm too is also easy to implement. If you look at it, it's just like a normal, DFS. It's a normal BFS, right? It's actually a very normal, BFS to implement the Prim's algorithm. Let's just walk over that very briefly. So this is a normal BFS. How do I know it's a normal BFS? So I can simply start with let's look at that. I can simply start with any node, right? So let's just choose node E, right? Let's just choose node A. Then you add your node A to your queue, right? So let's add node A to our queue. Then we enter a while loop. Then we explore all the neighbors of node A, right? Explore all the neighbors of node A. Here it is only 4, right? Only 4. Choose the cheapest. That means it's the 4 itself. Then, you select it and then you add it, right? So you add A and E like this, right? Then you come again into your while loop. Then you consider the nodes that you have chosen. Then consider the edges that have been selected. So you see, at each point, you're considering their neighbors, their most immediate neighbors. So consider all the neighbors of the nodes you have chosen, right? So I'll consider the neighbors of A. A is done, right? We are done processing the edges of A. But E has 3. So then, and that 3 connects to D, then I'll add D, right? It's a normal BFS, breadth first search. Then I'll go to the next one. I'll come again to have D added. Then I'll consider these neighbors and just like that. And that's relatively, straightforward. And then this is that. This is also something you can do with a normal DFS. And so I can just loop through it and then you're done. Now, let's talk about when they can ask you questions on minimum spanning trees. One, they can actually ask you like this same question we did, to implement cross-calls algorithm or something, and then we should be able to do that same for Prim's algorithm. But now let's assume they give you this question where there is a man, right? There's a very popular question called the traveling salesman problem and others, but let's not even talk about those now. So assuming they give you a question, there's a man who's supposed to, there's a post office man or a delivery person, right? A delivery woman. And then she has to, make all these deliveries to all these cities, right? To all these places. And each place actually takes time, right? To get there, blah, 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 or effort or something. But then she wants to make all these, deliveries and everything, right? They want you to find what is the cheapest cost, right? What is going to be the cheapest cost to, go to all these places, right? The cheapest cost to go to all these places. So that simply means that you're definitely going to, select a route, right? To everyone, but you have to end up choosing like the cheapest version of it. God willing, next week we're going to go through more into path algorithms, shortest path algorithms, and see how we can juggle the two together and solve problems like that. I'd have to let us go today because our number was relatively few because of people's exams. And go next week we go into shortest path algorithms and we should be good. But today I just want you to go feeling good about MSc and everything. And our assignments, we'll look up the time complexities of each of these algorithms. They're very simple to analyze. So I just want us to just go and look at it ourselves, try to code out the code. I can also send this week's problems, which involves writing out these algorithms, and then we should be good. Any questions? Does anyone have any questions? I'll upload the recording also. Does anyone have any questions? Anyone? Any questions? Oh, no questions. Oh, the last algorithm, the name, that's good. Honestly, I don't know of any official name for it. I probably should put my name on. Yeah, these scientists should actually put my name on. But I don't know the official name. I can check. Was someone talking?
So if you're given a question, do they ask you to like specifically implement Criscal or Prims, or do you have to implement the one you're comfortable with?
Yeah, so you implement what you're comfortable with, but some questions are easier using Kruskal's algorithm. And we will do one question like when we do shortest path algorithm. So one next week we'll do a certain question that you can either use Kruskal's algorithm or another variation of Dijkstra's, right? So like nobody's going to be like, unless the question is implement Prim or implement Kruskal, right? But it's just an algorithm, right? Just a way of solving a problem, right? So whichever works for you, you just utilize it, right? If you think about it, right, each of them has applications. For instance, assuming you're given the graph there, like select let's say the top five, like minimum like edge weight or something, then Criscal wins, right? But Criscal starts by selecting the cheapest ones first, and Criscal will easily help you get the top five, right? Prem is not going to do that, right? Like Prem just selects the cheapest for the nodes you have selected so far, right? Prem is more like a local guy, right? Like he starts by building the tree out, right? But Criscal is like this whole like roaming about, just roaming about the graph, choosing the cheapest so far, right? So you just have to choose which one, but no one really forces you to do that. But how we want you to think about the algorithm is think of it as a way of solving a problem, think about the parts and the logic and the intuition, and you meet other questions that basically apply them. Yeah. There's this other question we may do. It's a bit theoretical, but there's a question. I can just give you briefly the question. So you have the question is something like this. So you have a graph, right? It's called, it's an edge coloring thing, but a bit twisted, right? So you have a graph like this. What we want you to do is that we want you to, for every, so let's say there are two nodes, you can either choose a red node or a blue, right? And these are the constraints. Every red node must be, wait, must be connected by a blue edge and might be connected I think it must be connected to uh, to a blue node. Yep, to a blue node, right? And then both the edges and the nodes have weights, right? Then you're supposed to choose the edges and the nodes and then color them anyhow you want, right? But I want to use as minimum blue color as possible, right? I don't know if there's a right question, but I think so. And it's actually not an easy question, trust me. Like, it's actually not an easy question. We can take a look at it next week. There's also the edge coloring graph that you can also look at, but it's actually a variation of it, which is relatively harder. We can go through God willing next week, if folks want. And then yeah, we should be good. Sounds good. Okay, let's meet God willing next week. If you have any other questions, put it in the chat and then we shall get back